Welcome. In this video I'm going to show you how you can perform a Neyman Goodness-of-Fit test using R and my stikpetR library. This video will be using a Jupyter Notebook, but the code should also work in, for example, RStudio. I'm going to focus on how to run the test, not so much if you should be using this test. I'm actually currently running R version 4.3 with the basic packages installed. So, as mentioned before, this is a goodness-of-fit test, so you could also perhaps use a Pearson chi-square test or an exact multinomial or a g-test, or there are quite a lot of different variations on this test, and the Neyman is one of them. It's a little bit more obscure, it's not that often used, I think, but hey, you're here, so perhaps you're interested. So I'll load in some data, and I need a nominal field for this. I'm going to be using the MAR1, which is the marital status, and just to give you a quick impression, these were the responses. This was from the General Social Survey data from 2012. Now to load my library, it's not available on CRAN, so you will need to use DevTools, so install DevTools if you haven't done so already, and then you can actually just install this from my GitHub. Once you've done that, you can load it just as any other library, so I'm going to load it as well. The function of interest is Neyman Goodness-of-Fit. TS is short for test, and it requires the data as input. If you want, you can specify the expected counts, and if you want, you can use a continuity correction. There's actually only one Yates, there's no Yates 2. So let me immediately correct that, otherwise I get complaints. So there we go. And I already set my nominal field, so that's actually all I need to do. The result, as you can see, is a data frame that shows the number of scores we had, in this case 1941. There were 5 categories, that's the K. This is the chi-square value. The degrees of freedom, which is simply the number of categories minus 1. The p-value, in this case so close it actually listed as a 0, but it's 0.000 something. The minimum expected count is shown, the proportion of cells that had an expected count below 5, and a description of the test that was used. Now in this case the p-value is below 0.05, which is the usual threshold, and therefore we would reject the assumption that the counts basically are the same in all the categories. Now if, for example, these were our observed counts, but if I had expected these counts, I can actually list those as well. So I can create a small data frame with those expected counts and of course the categories they belong to. And then I can add that to the function by setting expected counts to that small little data frame. And now you can see that we actually have a p-value of 0.009, still significantly different. And if you want, you can also use different continuity corrections. I have Yates, Pearson and Williams for you available. So here's a quick showcase of each of them. In this case, actually all of them will be below 0.05, so it didn't really matter much which continuity correction I used. Alright, I hope you found this video helpful, and thank you for watching.